one, you're given a normal variable d, and you're given the mean and standard deviation. So you can just put this in your CAS. And so you want the minimum diameter such that um, is larger than 90% of the things. So we draw like a normal distribution here. We have some diameter d1 here, and the area behind it should be 0.9. So you do your inverse norm 0.9, and you'd get 6.83 centimeters. So this one is, it fits inside the container if the diameter is less than 6.95. So you put that into your CAS as well. And then for this one, you have a random selection of 4 tennis balls, so it's going to be a binomial. So let X be a binomial variable. And we have 4 trials. And then we know that the probability of some of a ball fitting through, like fitting into the container is this. That's going to be our p-value here. And then just solve that in the CAS. Is that first page okay? Okay. Um, so we have a conditional probability given that we want to find the probability that it's A, given that it's given that it fits, so 6.95. Okay. And then the condition for it being A is being within these two. So the intersection of those is just and so but then your CAS and you're gonna get so the we want 99% of tennis balls produced to be grade A. And the criteria for it being grade 8 doesn't change. So even after we change our standard deviation, um, it'll still be within these two. So essentially what it's asking is if this is our normal, this is our mean, this area is going to be 0.99, and you have your 6.54 and your 6.86 here. And you have to find the standard deviation which makes this area 0.99 for these two bounds. So what we'll do is the area of this and the area of this, they're equal. So say 2a plus 0.99 is going to be equal to 1. So you get your area to be 0.005. So you're going to use this in your inverse norm. And then, so we're trying to find the z-score for this. 6.54 minus the mean divided by our unknown standard deviation will be inverse norm of this value. And that'll be, and then you get your standard deviation to be 0.06 centimeters. So here we've taken a sample of 32 tennis balls, and we have to figure out the level of confidence. So the first thing we do is we're going to find p hat. And it's going to be the average of the two bounds of the confidence interval. And then our margin of error, which is z times the standard deviation of p hat, is going to be and then we can figure out the standard deviation of p hat just using like p1 minus p divided by n. So when you do that, you're going to get the standard deviation to be, and so then all you're going to do is just solve. And that's going to give you that z is 1.6443. So what that means is for our standard normal, we have our z is 1.64443. And here we're going to have the negative of that value. What it's asking us is what is this area between? Because that's going to be a level of confidence. So I guess you can just put that into the CAS and you get that it's like 0.89999 something. So it's 90% confidence. Does that one make sense? So probability that V exceeds 50. This one's just you evaluate the integral and you're gonna get 0.1345. And the exact mean is the expectance of V from 30 to 3 pi squared plus 30. So for this question, basically we're told that a graph or a function f is dilated by a factor of a from the x-axis or your horizontal axis and a factor of b from the vertical axis. So I went over this a while ago as well. But if our original area is a and we dilate by a factor of a in any axis, or like by some factor in any axis, we multiply the area by the same factor. And because we dilate it in both axes, we have to multiply our original area by a times b, and that's to equal 1. And we know our original area was also 1. Therefore, our first equation is going to be AB equals 1. Dilate this by a factor of 2 in the horizontal axis. The graph would look something like this. So if this y value was like y1, this would be 2 times y1. So then this area will be doubled. So the area under the green curve will be 2a. So the effect of the dilation directly affects like the change in the area. So if we dilate by some factor k in any axis, the area under the curve will also get multiplied by that same factor k. And from here, we can see that we've been dilated by a factor of a in the horizontal axis, and we've also dilated by b in the vertical axis. So what I'm doing is taking
Is it like to integrate g of w from 30b to b times 3 pi plus 30? Because the bounds get dilated as well. When we integrate you get 1.
that works as well.
Sure.
Say this is just our original area was 1, so I multiplied it by the dilation factors, and the new area also has to be 1. So I derive the relationship that A times B equals 1. So essentially they're just reciprocals. And then the next thing is going to be that,
Guys, you have to understand like what type of shortcuts he's keeping with his prior experience of rectification and stuff. So he knows like if you integrate it, you get it. But he's keeping these, small pieces so that he can do it like that. So that's the power of rectification. But it's going to be too late because you can see it's coming.
so let's say our probability density function looks something like this. And then we want to dilate by a factor of B in the vertical axis. So it becomes maybe something longer like this. If this is where our mean is, I guess when we dilate in any axis for probability density function, even though like the curvature of the function changes, it still like preserves, I guess it still preserves its qualities. So this new mean here will be directly affected by your translation. So what I mean is, if we take this previous mean here, and then we translate it, it should fall upon our new mean because it like directly affects it. So then when you solve this, you get B equals 213. So it's like as an example, let's say the mean here is at 1 comma A. It doesn't matter what A is. The mean here would be at 2 comma A after we dilated by a factor of 2 in the vertical axis. So what I'm saying is that when you dilate by a factor, all your important points will remain important points after your dilation. So you can just directly dilate your first original mean, equate it to the new mean, and then you can solve for B that way.
So you guys understand what he said? He said this important after dilation, the important properties stays the same. Because once you dilate it, the new curve is a probability density function, right? If it is a probability density function, symmetry should hold true. Area under should be 1. So those properties should be the same. So that's why, as a summary, he's saying specifically if you transform a probability density function, then under transformation, those features are going to be the same. Yeah. So he knows it as a fact now. So now you have to know as a fact now. Go home and consolidate that.
And then obviously if B is 2 on 3, then A is a reciprocal, so it's 3 on 2. You can also take like an integration approach as well, which is if we know that our transformation is W prime is W times B. So I'll clear this graph. Then 3 pi squared plus 30. B is going to be our new upper bound, like our new domain value. And 30, B is going to be the other value. So if we integrate 30, we integrate, sorry, G of W from these bounds and equate it to 1, that's total probability. And then if you do the same thing, if you solve this is equation 1, and this is equation 2, it should give you a value for A and B as well. But it's just a lot longer and messier. So is there any other questions that I should go through? Find 15T. And obviously we know like if the Ferris wheel is moving around, our W of t has to be a continuous function because like if it wasn't continuous, you kind of mean like the carriage doesn't work. So h of 15 should equal k. So you get k is 135. And then if it's going 2 times faster, then we've dilated by a factor of 2. Therefore, m is 2. So that's fine. So what we know is that at this point as well, there should also be continuity. So h of 20 times 2 plus n should equal 135. And actually, you can just solve that in your CAS and it'll give you that n is 5 plus 30k. Does that make sense?
Like that.
Yeah.
I think that M equals 3. That's when like
So we're told that it's moving at double the speed, right? So then we know that if it wants to complete half a rotation twice as fast, the period has to get halved as well. So to half the period, we need a dilation, like m has to be 2. 3GH. So there are certain like situations where Newton's method fails. So Newton's method fails at like stationary points, right? So if this was like, I don't know, x1, you can't use Newton's method at x equals x1 because you get a horizontal line, and a horizontal line can't like it can't intercept the x-axis, so then Newton's method will fail there. And what you find about this expression is that h prime of x is also ln to 2 to the x minus 2x. So we see that this expression is actually the derivative equal to 0. So we know that any solution that you get from that equation will correspond to a turning point, right? So then it'll lead to you getting a horizontal line, and then Newton's method will fail. Does that make sense? And then for this one, I think if you solve it on the CAS, it'll give you an approximation for Euler's number. But first thing we'll do is we'll try to reduce it by hand as much as possible. And then if it's going to be a local minimum, we can equate the derivative to 0. And then what I'm going to do is I'm going to isolate n to the power of x because we have n to the power of x here. So we can get the n to the power of x is going to be n divided by ln n x to the n minus 1. Now I'm going to sub that in to f of x, which equals 0, which would then be n divided by ln n x to the n minus 1 minus x to the n. So then I'm going to factorize that as well. And then from there, we get that the x coordinate where this happens, like where I guess the point that we're looking for is here. So does that make sense until this point? Okay, and then we're going to find f of this. So you can put that in your CAS, and it will give you e to the n minus n divided by ln n to the power of n. So what we can notice here is that if this has to be equal to 0, and these are both to the power of n, then you can equate the insides. So e will be ln n divided by n. And I think you can put this into the CAS, so you can just like observe that like when n equals e, the condition is satisfied. I'm pretty sure like if you solve this directly, it won't give you decimals and it'll give you like the exact value of e. Does that make sense? Oh, how did I equate this to 0? Because we're told that the local minimum has to occur on the x-axis. So then the y coordinate is 0. Is there anything else?
Wait,
Last page. So for this one, we find for our original function f of x that its turning point is at x equals 0.
Yeah.
We find that our turning point is at x equals 0. For this one, because this is straight dilation,
Guys, some people can't hear.
the turning point is at x equals 0, and then g of x is a turning point at x equals 2. So we can see that like the turning point moves with the translation. So then here we know that at x equals k, we're going to have our turning point again. So then if we sub in h of k, it's going to give us 2 divided by k, which is the same thing as 2 times k to the minus 1, right? And then, I mean, you can just match minus 1 to n, therefore n equals minus 1. Does that one make sense? Okay, so for this one, we'll consider like for k equals 1, the graph will look something like this, and this will be the line y equals x. And so the inverse and like the actual function itself will come into contact first on the line y equals x. You can know that because this is an increasing function, so it will always be on y equals x. So then what like the idea would be is you'd solve for it tangentially. So you'd solve h1 of x equals x, and then h1 of x prime, so the derivative equals 1. So you want it to lie on this line and also be tangent, so to have the same gradient here. But when you solve that, it actually, I'm pretty sure it doesn't work. I think it gives you like a negative value, but we're told that k is greater than 0. So instead, what we're going to do is we're going to do the same process, but we're going to do it manually. So instead, what you're first going to do is take this equation and solve it, and it'll give you the x is plus and minus k squared plus 4 divided by k. And what you see is you have to choose the positive value of x, because when k is greater than 0, obviously a square root will be positive. And if k is positive, then you want your x-intercept to also be positive. So you're going to choose the plus version. And then you're going to solve, you're going to put this value back into this first equation, and then just solve for k, and it'll give you k is 1.27. So I guess the reason this doesn't directly work as a simultaneous is because it's just too demanding for the CAS to solve.
Check that in mathematics and tell me, okay?
So for this last one, I mean, we're given the value of k is 5. So you see that I think g of x looks something like this, and the inverse has this sort of shape. So you find your x1, your x2, and the area will just be what is h inverse of h1? The h1 inverse of x minus h of x dx from x1 to x2. That'll equal, I think it was 43.91. Or alternatively, you could write this down. Like you could find your x-intercepts and write it down, but you can just go to the graphing page and just find the area that way. Either works. So is there anything else I should go through?